Good morning, everybody. So I'm here now to walk you through how to look at bigger data, like an exome. So yesterday we did the targeted panels, which has a lot fewer variants than what you'll see today. So, what? Can you hear me? Um, so I had a couple of questions from people going around yesterday, like, are they all this easy, or is it all, it's all. So no, they're not. And so in case anybody thinks they're ready to, come take over our job, I'm going to take you down a notch. Um, so, yesterday we were looking at tag scans, which is maybe 8,000 variants, and we showed you how to filter through some of that. And probably you saw a lot of, even after you put on the filters, you're seeing some noise, some calls that if you look in IGV, they're not good calls. And hopefully you're comparing different samples, not just looking at your one sample, but if you have up a few samples, you can see that, some of these calls are noise in the gene, just noise. And so there's a lot of that, but there's also just variant noise too. And so we'll show you how to put in, if you're fortunate to get parental samples, that helps a lot with the analysis. And I was going through our database trying to pick a few like a couple trios to just kind of walk you through how to look at a trio. And by far and large, almost all of our diagnostic cases are de novo variants of, they're private de novo variants, which are just super quick and easy to find. So it's kind of, it's not rare, but it's less common that we have a real recessive case where each parent is a carrier of something, and then you've got, a kid with a recessive condition. But not that that doesn't happen, but I'm just saying most of the cases in our database are de novos. So it's really helpful to have the parents in those situations, because a lot of those de novo variants that we know are de novo because we have both parent samples. If you don't have those parent samples, it may just be some rare missense variant that no one's ever seen before, and you don't have anything else to say about it. But if you can say that it's de novo, and it fits the phenotype and it's absent in population, then you're able to call it likely pathogenic. So it's a huge difference in everything. So exomes are around 150,000 variants is what you'll have today. So again, you're just looking for these needles in a stack of needles. So some differences that you're going to see. Tag scan, for the most part, the targeted panel, we had pretty good coverage for most of the genes on the panel. So, you're looking at 100x or 200x of that. The exome is going to be lower, so it's going to be something around maybe 80x. But there's also going to be regions that aren't well represented because of the enrichment technology that we use, and just some bias in the whole in the technology. So you're also going to see some more garbage calls. If you thought you had some garbage in the tag scan, there's a whole lot more garbage in the exome. You're going to have more variants. And you're going to have a lot more genes that don't have a good gene-disease association. So we'll kind of go through analysis by inheritance pattern again. I'm just going to walk you through a couple of examples, and then my plan was to try to go in live and show you how, just kind of step-by-step show you in Viking, if it cooperates. But here's a case we had recently. It was a male patient that was referred for a symptom-driven exome. So when we do an exome, we only look at genes that are relevant to the patient's reason for referral. We're not looking at incidental findings. We're not looking at off-target carrier status kind of stuff. So if it's a gene that potentially fits the patient's phenotype, then we're gonna look at it. So these are the HPO term, or these are akin to the SAGA terms, but this is just a different medical vocabulary. So these are HPO terms. So there's a long list, but basically he has a neurological condition where he's got autism and seizures and developmental delay. He's really thin, so he has, they were really working him up for a lipodystrophy. Like, he has really just kind of an asthenic body habitus, so just very thin and no body fat. And a little bit of maybe dysmorphic features. So just kind of walking you through this without showing you all the stuff. For as far as variant counts go, once you put on the filters for 1% frequency and looking at just category 1 through 3, in this case, we had 132 variants left, which is pretty typical for an exome. And that's a good sanity check to make sure, like when you're working on cases, if you're going from case to case and maybe you have some filter on that you forgot, when you apply those initial filters, you should have around like 130 to 150 variants for an exome using those filters. Unless it's, I should say that that's for probably a Caucasian. For somebody of a different demographic, potentially it's more. After we apply those saga term filters that I showed you, then we still have 47 variants left over in this case. There were several variants of unknown significance that were overlapping with the phenotype. There were many, many, many we could just eliminate because they're not looking like they're related to the phenotype. There's many others that are easy to dismiss because they're benign because of the allele frequency in nomad, like what you looked at yesterday. There was one X-linked missense variant that was not present in the mother. So here's what this looked like here. So these were all variants of unknown significance that we reported. So we have a coloring system. I don't think we even talked about coloring yesterday, but if you right-click and you say add to variant different category, you can color these just so you can kind of mark them when you're going through. So we mark things that we think might be likely pathogenic as orange. Yellows are going to be variants of unknown significance, and blues are benign. So this is how we marked this one up. So this one at the top was interesting because it's not present in any database. It's category 1, and it was absent in the mother, and this is a male, and this is an X-linked variant. And so for a second I was thinking, oh, we could potentially call this likely pathogenic if only we had the dad and we could show that this is de novo. And, you just have to remember your genetics from now and again. So, if you're a male, you're only getting a Y from your dad. So really the dad doesn't even factor in here. So we called this de novo even though we don't have the dad because it's de novo. It's not present in the mother and it's an X-linked variant. So this is one of those, like, I need to stop working and take a break. So this is the gene. It's SMS. It's a X-linked variant, recessive condition that causes something called Snyder-Robinson type mental retardation syndrome. And so this is a proline to a leucine at 281, and it's predicted to be deleterious and damaging by in silico tools. And if you look up the OMM clinical summary, you can see there's some overlap. This is not a super specific thing, other than the kind of the lipodystrophy was pretty, that's a pretty not specific thing, but it's not present in every intellectual disability syndrome. So I'm just showing you how we went about assessing this variant. So we called this de novo, and it says paternity and maternity confirmed, which isn't exactly true, but it kind of doesn't matter for this case. And it's absent in population databases. We had in silico tools calling it pathogenic. I'm not going to really use this one. I don't really need it, so we're calling it likely pathogenic based on those things in the blue. So, and that's when, we called the clinical geneticist, and, sometimes you think you know what they're going to say or if they like, if they like it. And he said, this one, it looks like he read the book about this. The patient read the book. So they like the diagnosis for that one. Okay, so this is a different case. And this is a research case that we had, and this is a trio. So when you go to load a trio, I'll try to show you this live, but under analysis, you're going to say load multiple samples up here instead of just one, and then you can type them in. And then, so you're going to get all three. You're going to get the parents, both parents and the child. And then there's a set query feature that we use, which is under analysis. Again, so you're going to go under analysis, and you're going to choose set query, and you're going to put that you want the variant to be in the child, and you're going to leave it blank for the parents. Because if you want to be too strict and say this is going to be absent in the parents, then you can change it and look for de novos that way. You can say that it's not in the parents, push that, and then that's a way to look for de novos. Okay, and then to establish your familial relationships, we want to set up the pedigree. So under analysis again, you choose pedigree, and then you're going to say that which sample is the mother and which sample is the father of this case. Okay, and then if you want to select an inheritance pattern, you can say, I'm going to look at de novos this way, or you could also do it the set query way, where I showed you, you say it's not in the parent samples, and then um, you choose set query, or you can choose de novo here. But when we do that for this case, we're still having 49 variants with the Omen filter saying that they're de novo. So in an average genome, you only have a few de novo events, period, in the whole genome per generation. So this is a lot of noise. This is not all real. So you can see some of these have very low allele fraction. So this is like 6 out of 19, 5 out of 18, 4 out of 12. That's noise. And you could set your filter higher to say you want to see more than 4 reads for your variant that you're looking at as far as quality, but then you just run the risk of missing something with lower coverage. Okay, and then to set the phenotype filter for this one, this child was referred for hypotonia and intellectual disability, so we're setting that. And then we're going to say, oops, sorry. And then if we select the phenotype filter by setting the saga here, then we're down to only 7 de novo variants. So these are all variants that are clearing the phenotype filter. So at least one of these genes, or at least all of these genes have at least one of the features of hypotonia or intellectual disability associated with it. So you can go down the list and do what you did yesterday. This is a shorter list. You can say, well, this is an ataxia gene. The patient doesn't have ataxia. You can just do kind of a check about that. This one is a variant that you can see is present in only 2 samples out of our whole database, and this is them. And this is the same patient twice. So it's present twice in our database, but it's the same patient was run twice. So this patient was first run as a clinical targeted panel where we found the variant that we found. And then he was enrolled in a research study where the parents were also enrolled. And we recommended on the clinical report of the targeted panel that it would be nice to have parent samples, and we could maybe show this as de novo. And we did, but we did it by doing a whole exome on the parents, which is a little bit of overkill, but it worked. So here is the de novo call. So there's this is the patient, and you can see it's absent in both parents. And what you would want to do to assure yourself that you're looking at the right sample identities is just look for some rare variants that match both the dad sample and the mom sample, and just make sure that there's some relationship there. Here's another variant that was present on our list of 7 variants where you have kind of a, yeah. Oh, so, yes, yep. Everybody has rare variants, and you just want to make sure that there's some that match the other. Yep, exactly. It becomes pretty obvious when you've got them in Viking and you've got the parent and you've got the child and both parents, and somebody's, if the parent doesn't have any variants that the child has, that's a problem. That's too many de novo. So here's an example of a call, and you might see this where it comes up on your de novo list, but it's really not de novo. You can see that this call is present not just in the child, but in both parents, so it's just kind of just an artifact. Okay, does that all kind of make sense so far? Yeah? Yep. No? Oh, yeah. Sure. No, I can't think of any. I can't think of any that we've had. Okay. Uh huh. Uh-huh. Yep. Yes. It's a moving target a little bit. So we set the variant threshold at 4 because there's plenty of places in the genome where you don't have that good coverage and you don't want to be. I mean, we've had a lot of cases where you have 5 reads being called for the variant, and maybe it's out of 10 or 12. So it kind of depends on what's the allele fraction, you know. If you have 5 out of 50, you're not going to be that interested. If you have 5 out of 10, I would look pretty carefully at it and Sanger confirm it if you feel like you need to. Okay. So I'm in yours, right? Regular Viking. Yeah, I'm just going to go to regular Viking. Yeah. Any more questions while this is going? So even if we throw a whole exome or a whole genome at a patient, the best detection rate, or as far as diagnostic rate, we really hope for is about 30%. So somebody was asking me, the question about is it always this is so easy, that's right here. It's, well, you're looking at cases that all have answers, which is only about 20 to 30% of what we look at. So I think it would be not that good of a session for you if you're just looking at lists and lists of VUSs like we do all day. You would be not happy with us if we gave you those. So. Well, we come up with gene lists. We take off the gene list filters. We look for all of our checklists, and we report out variants that meet our reporting criteria, and a lot of them are going to be VUSs. Okay. So I'm going to show you, as far as loading multiple samples, we're going to do that now. So under analysis, you go to load multiple, and you're going to hit the add button. And I'm going to search for something I want to add. And actually, I'm going to show you a recessive one that does not have parents with it. I was thinking it did, but I think it's a good, easier one to start, and then we'll do a more complicated one after that. Ooh. So this is actually the very, very first exome we ever ran here. So you can see this dates back to 2012.
So if you're remoted in, this isn't.
Oh yeah, don't.
You can't load this one. So that's
I'm just walking through something.
To force you to watch.
Sorry.
Not our first
I think I might be frozen. Am I frozen? Oh, no. Okay. Move. I'm going to add, actually, we have her sister too. Numbers 1 and 2. So we did get the parents of these girls, but we did not run exomes on them, so their data is not in our warehouse. We only did Sanger sequencing for the variant that we found in the girls. So these are two girls with intellectual disability and ataxia, like a progressive ataxia with cerebellar atrophy. Um, okay, so I'm going to go to set query, and I'm going to say, I'm going to make this easy, and we're going to look at only variants that both girls have the exact same thing. We're going to only look at things that are present in both of the girls. So I can say the variants in both of them, and I apply that. And I'm not going to do a pedigree because we're not setting up, parent-child relationships. But if I were, I would go under analysis, pedigree, and do that here. I would call mom and dad, but we don't have that. Then for the sample, I'm going to just pick one of these, and I'm going to say I want at least, I'm going to say 5 reads just to cut out some of the noise. We have ACMG 1 to 3. I'm going to put in some SAGA symptoms for them and make sure I'm in the right kind of SAGA first. So this has to be on SNOMED. I'm going to load the symptoms here. So I'm going to go to neurology. I think. Am I just skipping it? Okay, I'm going to say actually, I'm going to take off intellectual disability because that gives tons of, you probably saw yesterday, some of the terms will call up a lot of genes, and some of them are more specific. So intellectual disability will give you hundreds. Ataxia, not as many. Something like a cherry red spot gives you only 2. So it just depends on your terms, and like we said yesterday, they're additive, so the more terms you put in, the more things you're going to get. So I'm going to make it pretty restrictive because I know ataxia is going to give me the right answer, just to show you it can be easy. Darn it, I just passed it. So here's ataxia. And then I'm going to close that, and I'm going to turn on this SAGA symptoms there. And so, let's see. What have I done here? Okay, so I still have 23 variants, but that's out of... Oh, I did? Oh, that's why. Okay, thank you. I'll take that out. It seems like what? A minefield? We read the clinic notes and we use our judgment. And then in the end, the next one I show you is not going to be so straightforward. And so there are plenty of examples where your gene is not going to come up with whatever symptoms you have. And it could be that your patient has an atypical phenotype and that those symptoms of your patient haven't been mapped to the gene yet. Or it could be a new gene, it could be lots of things. So in the end, if we're not finding something, we're going to take off the symptom filter and kind of make sure we're not missing something, either a new gene or something that could have some overlap that's not being captured by the SAGA filter. Okay, so this should be a little bit more restrictive. Okay, so now only 7. So these girls are like school age, like maybe around 7, so they're probably less likely to have Tay-Sachs, and this is a plus 30 variant, so that's pretty deep in the intron. We wouldn't even report that unless it's a note, well, I should say, we would investigate it if it's a category 1 because there are splice variants very far out in the intron that have been, reported. So, I mean, you just need to go down the list like you did yesterday, kind of correlate what is the features of your patient. These are all actually category 1, which is, oh, wait a minute. We didn't put the, We didn't put the frequency filter on, that's why. So now we're left with only 3 after we filter for frequency. So this looks super easy, right? You've got a category 1, a homozygous variant and it's a premature stop in a gene that causes ataxia. It's a progressive type of ataxia. And it's present, it's homozygous in both sisters. So that's an easy one, right? This gene, I don't know. This is citrullemia. This is a stop mutation actually, but they don't have this. So that can be very straightforward. If you take off your Saga filter, you're going to have 150 variants to sort through. Maybe not if you're insisting that both sisters have the same variant, but it's not that often that we're doing something other than a parent-child trio. It's not that often we're getting multiple siblings. Okay, so let's do a more complicated one. Let's see, load multiple.
While Carol's loading that, I'll just mention we're going to show you guys something called Phenomizer that is completely separate from our delivery system. For your cases that you're going to do this afternoon, we pre-created gene lists for you using those terms because it's a little wonky for you to do it separately, but we're going to show you how you can do this using this other tool. That's actually much easier to use than the terms we've been showing you. That's searchable and has tree logic and is much more, it's less boring.
Mm-hmm.
So
Yeah.
we'll show you that.
So when we're doing a real case, we use Saga. It's a different version of Saga where we're using HPO terms instead of SNOMED terms. But so it's a little bit more searchable and user-friendly. But we also use Phenomizer. So we might end up loading a few different gene lists based on, some commercial labs have big panels of autism genes or whatever. Sometimes we use other people's gene lists that we find, or we make our own, or we just kind of throw everything we can at it. So we're going to load this one. This is a child with her parents, and this little girl has what was suspected to be a mitochondrial myopathy. So she had muscle weakness, intellectual disability, seizures. She was thin, kind of failure to thrive. Okay, so I'm going to go under analysis, and I'm going to set my query to say I want it in the child, only the child. And I'm going to set the parents up. This one is the mother. Oh, wait. Sorry. That's the child. This one's the mother. And this one's the father. Okay, so mom and dad are in there. Okay, and I'm going to put in some Saga terms. I'm going to put in intellectual disability because you know how nonspecific that is. I'm going to put, I think she had some involuntary movement. She had some muscle weakness. She had epilepsy. So these are all things, this should come up just hundreds and hundreds of genes. I'm putting the Saga filter on. Okay. Everybody happy with that? So we could start out looking for de novos. I can tell you it's not a de novo. This is a recessive condition where both parents have one of the variants. So the way we would go about this is just how you did the tag scan, only on a bigger scale. So we would look at things that have been reported before and loss of function variants that match the saga terms, right? We would go through all those motions. You can see that so this patient is African American. So this is a good example of things that are very rare in our database, or pretty rare, are very common and exact. So this one, it's reported as a disease-associated variant, and it's present in 5% of somebody, and the highest frequency of any group in Nomad is 5%, and it's going to be African American. So, you can go through and just dismiss most of these. These are over 1%. You just going down the list. I mean, we can't take all day to do this. You can see there's no category 2s, which means basically just loss of function variants that haven't been reported in the literature that match your phenotype filter that you have on, right? So I didn't know I looked at this morning and I wasn't sure if our gene would match the phenotype filter at this point because it's a new gene. When we analyzed this case, it wasn't an OMIM-associated gene because we're the ones who discovered it. So at this point, it's in OMIM now, but it's still one of those genes. If you saw any of them that have a question mark by them, it's because OMIM feels it's not, maybe only one publication is there, and it's not enough data at this point to be more definitive. But this one, it's definitive. We actually know about another case in Japan that I thought they were going to report it, but they haven't got it in the literature yet. So still, ours is the only case, and it's this girl. So we can't go through every single thing, so I'll just take off the saga filter, and I'm going to put on the OMIM filter because, yeah, it's in OMIM. And so it's like what I was saying, a good sanity check when you have the filters on that we have for OMIM, CAT 1 through 3, and MAF of 1%. For a Caucasian, you expect around 150 variants. For an African American that you're filtering off of our local database, you have 326. So it's a lot high, it's double, because a lot of these are in Nomad as very high frequency. So they're going to be not anything to look at. If you kind of go down the list, so if it looks like this is a lot of work to go through all of this, it is. I mean, it can take you a whole day to do an exome if it's a difficult one. So yeah, we're taking applications. So if we go down here, you can look at the CAT2s. So, a lot of these you could dismiss, and again, it's familiarity with the genes in the genome, and you don't know every single gene in the genome. We've been doing this for years, and we still don't know every gene in the genome. So that's what the OMIM clinical synopsis is very handy. We use that a lot just to get a feel for, is this something that could be related? And you have to be careful about, you want to have a little bit of leeway for broadening phenotypic spectrum or just atypical patient that's not reading OMIM what they should be like. So if we go down, where is our gene? I'm not even seeing it in OMIM right now. That's all right. 193. Yeah, that's what I was saying. We're skipping the de novo because it's not de novo. Yeah. And I don't know why I have some filter on that. I'm gonna take this on and off. Sometimes things get stuck and you need to take it on and off. So yeah, you can see a lot of these CAT ones are just really common. This one's 7%, this one's 10%. So that's not anything you're going to be interested in. Okay. Another thing, so after you do your de novo check, another thing to do, you just got to make sure you remember which filters you have on and what you need to take off for your next step or your next patient. You can say that you only want to see things where either you have a homozygous variant or you have at least 2 variants present in the same gene. So you can check this box that says restrict to genes with homozygous or compound het variants. So that's a good way to kind of look for recessives. The only thing to be aware of is you could filter out a heterozygous variant where you have something on the other allele that you're not detecting by NGS. So it could be a deletion or something like this. So there's that. And there are some conditions where even though the patient has a clinical diagnosis of this and they've got one pathogenic variant in this gene that goes with that, you still have a detection rate of not 100%. And so there's, maybe there's something deep in the intron, maybe there's just something that's not getting detected for whatever reason, for whatever method you're using. Okay, so we have this filter on, and then at this point I would sort by the gene name so you can see in order. It's going to give you alphabetical order of the gene, and whatever variants are in that gene are going to be right next to each other. So if you have 2 genes in, or 2 variants in ADGRV1, then they're all going to be, here you have 3. So you're going to have you can evaluate them all together, So we're going to just keep going down the list. And a nice thing to do might be to highlight any loss of function variants that you're interested in, like highlight them yellow, and then when you're scrolling down, it'll really come to your attention, oh, here's one that's interesting, and is there another one in the same gene right below it? But I didn't do that, so we're just going to skip down. And so down here, there's one that starts with P, and P. So yeah, I mean, it can be pretty onerous to do an exome. So here you can see this is PNPLA8. It's associated with mitochondrial myopathy with lactic acidosis, and it's a CAT1 because we reported it. And you had 2. So what got our attention about this, even though it was not a known gene at the time, was the fact that this little girl has 2 loss of function variants in trans with each other in a gene that if you look at the biology of the gene, it's a mitochondrial gene, and it seemed like, it could fit. And this is one, so this is an example of trying to chase down, is there a gene disease association here? So we contacted a researcher who was willing to work on this, and he already had a mouse model and had been working on the enzyme for 30 years, and it was just a great collaboration, and it was, relatively easy. And we sent her a muscle biopsy of the girl and was able to show diminished PT protein, and yeah, so we worked it up that way. So if you were to click on this one and look in the warehouse page, there's 2 samples with this variant, so it's going to be the girl and one of her parents. And we ended up genotyping the rest of her siblings, and everybody was either a carrier for one variant or negative for both, so it's tracking in the family as it should. So here's the variant. The gene is PTPNLA8. If you click on the OMIM, there's a clinical synopsis based on our 1 patient at this point. So, but in course, Isabel was corresponding with a guy in Japan who has a patient just exactly like her. And what also gets your attention is the fact that the frequency in all the databases is basically 0 for a loss of function variant in this gene where the girl has 2 variants in trans. Any questions about, we'll walk around, and Sarah wants to make sure that your laptops are set up for the workshop. Any other questions before we just launch into the workshop?